Okay, well, welcome, sports fans. As Goose said, well, it's the bottom of the ninth. The score is tied, and it's time for the big one. And we're talking about 2 and 3 engine out contingency aborts. So I'm going to share a little personal story with you, and I don't know. Let's see where that picture goes. Should be able to see this picture. If you see this picture, this actually says STS 51, and it has a name Tony, and wearing a black shirt, and that is what I'm wearing tonight. And then if you can look at the video, which I think I can see, I have a white shirt that has Andy in the STS 51. And this came about because during STS 42, I was working with Ron Graby and Bill Reed in the Contingency Aborts, and we were debriefing, and over again, Ron Graby kept calling me Tony. And so I let it go for a little while, and then finally I stopped him and I said, Ron, my name is Andy. It was real quiet for a second, then Ron came back and said, oh, well, I thought it was your evil twin brother, Tony. And so Reedy was again on the STS 51 crew, and he and I are pretty good friends. So when they started training, the 51 crew gave me a white shirt and a black shirt. And so whenever they'd hear that I was down on the sim floor, they'd always ask whether it was Andy or Tony who was down there. And I didn't necessarily tell them it was Tony if I was going to give them a contingency abort. They generally knew if I was there, I was probably going to do something like that. So what we're going to talk about tonight are Space Shuttle 2 and 3 engine out contingency aborts. This is going to be a rather long one, and it just makes sense to kind of run through all the material at once rather than break it into two different parts. So about halfway through, we're going to take a 5-minute break and let everybody hit the bathroom, get a drink of water, and all that kind of stuff. I think most of you already know why I'm giving this briefing or what I used to do. For about 25 missions, I was like the sole training guy doing this kind of stuff with the crews. And so without further ado, we're going to talk about why these maneuvers exist and what the basic objectives behind them were. I'm going to talk quite a bit actually about the history and development and the rigor of the supporting analysis behind them. We're going to take a look at some basic maneuver sequences that are used throughout and what they're trying to accomplish. And of course, we'll always look at the flight data file. But the other thing we're going to do that we haven't done in previous briefings, because we're going to talk about manually flying these, which is how we first started off, is to kind of run through quickly the orbiter controls that were used to execute the procedures. So what are contingency aborts? Now, the way that I'm using this term, contingency aborts in general in shuttle aborts could be for massive systems failures, but we're talking about 2 and 3 engine out scenarios where you don't have any completion to just coast to a landing from where you were. In the TAL briefing, I talked about some things called single engine completions. We're not going to discuss those. But the cases that we're going to talk about tonight are 2 engines out before a single engine completion for on the TAL or a nominal, with one exception, that's RTLS, and we're just going to kind of mention that. We're going to talk about 3 engines out in all the profiles. And then these procedures also covered 1 engine out and 1 stuck in the bucket, which was kind of an abnormal engine configuration. So how did these things begin? Well, the initial analysis began in December 77, and they started trying to develop procedures to glide the orbiter to get it into an ejection envelope for STS 1 through 4, where we had ejection seats. I kind of mentioned that during this training, when I was doing the TAL briefing, they did an abort to rota, and they figured out that they could actually lob the orbiter across the ocean and land. And that's where the transoceanic abort landings came from. And then the automated TAL was first on STS-3. So they kept working these procedures till about STS-5. And then as the ejection seats came out, they kind of lost interest and fell by the wayside. The crews were always interested in what could we do if something happened and kept exploring it. And after this time period, there were also got people from Mission Ops Flight Dynamics Division involved, the astronaut office, and then kind of later on, primarily after Challenger. When I was there, the training division got involved in actually investigating this area and expanding the envelope and trying to make these things work better. And we'll talk about why it was so important after Challenger in just a minute. So the initial procedure development was always in the SMS. It's just when the crew, that's what the crew had access to and what they could go fly. Eventually, later on, again, after Challenger, we started working some in the SCS, and we actually did not only procedure development in the SCS, but we also did training in the SCS, the Shuttle Engineering Simulator over in Building 17. Up until Challenger, all the engineering support was informal. We discuss it with different analysts or the crew. We do back of the envelope kind of analysis to kind of figure things out. But the way the procedures would come about would be just getting in the simulator and trying something and seeing if it worked. And so, and in the early days when I first got, the first time I ever saw one of these was when I was training the 41G crew, and I was there when Crip went through his training. And actually at the time, Crip's attitude was, this is like practicing bleeding. And the reason he felt that way was that orbiter handling in these regimes was very poor. And what I didn't know till later was it's because the aero databases really didn't support what we were doing. And so, of course, the vehicle handling is very poor in those regimes. And it was not likely the crew was going to survive those, at least from what we were seeing. The structural and Q-bar limits that we used to kind of hammer out what we thought the maximum G's were or the maximum aerodynamic loads we could take during the pullout, which is the major thing you have to get through, really were based on, again, back the envelope kind of knowledge of the design and the aerodynamic end. Really, we didn't have any aerodynamic analysis on the structure. What we were looking at was, could the flight control handle the actual pullout? And what we were consistently seeing was that around 800 pounds per square feet during the pullout, if the aerodynamic forces got higher than that, it would just overwhelm the flight control system and you lose control of the vehicle. And so we adopted that 800 PSF limit based on what we were seeing in the sims. So then we had the Challenger accident. And of course, the big recommendation that came out of that was we needed some way for the crew to escape. And they've tried to, obviously, first stage was where you'd love to have it. But the recommendation to improve crew survival, NASA went off and looked at. We actually did go off and look at vehicle redesigns. We talked about putting ejection seats for everybody back in the vehicle. And the bottom line with all that stuff was that where the vehicle was at this stage, it really was prohibitive to do any of that. It was going to cost too much money or put the program down for years, and we're talking more than a couple. And so the decision was made to do two things. One, to try to improve contingency abort development so that you could fly the orbiter through these regimes, hopefully, and survive and get to an entry. And then on the entry side, at least initially, what we were looking at solely was up until this point, all of the contingency aborts had resulted in a ditch. And obviously, we had a lot of discussion about would the crew survive those. I don't think very many people thought that they would, because generally they're hitting the water with all the payloads in the payload bay. And so those things are probably going to come loose and come forward, and the cockpit was not going to probably be in very good shape. Plus, what they told us in my Navy background was if you hit the water at anything over about 150 knots, the aircraft probably isn't going to survive it. And I know from personal experience that that's true. Not that I did it, but friends of mine did. So all that together said we needed something other than ditching the vehicle. And so what we did was we incorporated a bailout system. We're going to talk about that just briefly. And actually, after thinking about it, I'm probably going to do another little briefing on bailout systems later. But the objective right after Challenger was to improve contingency boards, get them to the point where we could at least get to a bailout, and we actually were able to take it further than that. As part of the whole engineering and analysis effort to improve and give us more rigor, along with a lot of aero database development and testing that was going on, we were flying these mock regimes at high alphas that we didn't have anything for, and so they were getting us more and more and better data. they did what they called the vehicle abort capability assessment. And this was the first time they'd gone off and looked at some of the loading that with the data they were pulling out of simulations and trying to figure out what could the orbiter really withstand. And I mentioned to you that we were using an ultimate Q-bar limit during the pullout of 800 PSF to call it survivable or not. What we found out with this particular assessment, and one thing we hadn't thought of, or nobody really thought of, was that at 750 PSF or higher, you risk ripping the nose cap off the vehicle. So that became the upper limit for survivability. Our back of the envelope G level, we thought that we could probably pull about 3.9 to 4 before we actually started breaking things in the wings. And when they did an analysis of that, they gave us a 3.5 to 4.2 G limit, but that was based actually not on the wing like we expected, but it was based on the OMS pods. And the G limit for each particular mission would be variable because of the mass properties of that particular mission and what that would do to the orbiter. So during this era that I'm talking about right here, all this stuff was manually flown, manually trained, manually flown. And so we were, of course, you know, computers were getting more and more improved. Now, we didn't really change the GPCs, but again, we started looking at could we automate these procedures and essentially make our chances of survival go up from here. And so the program actually pursued automation after a lot of debate, and we automated them for 2 engine out with a software drop, and each software drop was called an OI, operational increment. So OI 22, which hit the streets in 1992, we automated all the 2 engine outs. So we had a period where the 2 engine outs were automated, the 3 engine outs had to be manually flown, and I'll show you procedures from all these eras I'm about to talk about. Then finally, we got the 3 engine out automated via OI 25, and this was 1997. Now, in the era where we were having the 2 engine out automated, the flight directors were really curious to see what we were getting out of it, and so they would have me track success rates in the simulators, and we were actually seeing simulation or success rates in the 80% range. I'm going to caveat that by saying 2 things. Number one, when you take a crew into a scenario, you don't purposely give them one they're not going to survive. And so I'm purposely setting up training scenarios where I know I'm probably going to get a success. So that's number one thing to keep in mind. Number 2, the elephant in the room for contingency aborts. Always, always, always. You had to get benign engine shutdowns that did not impart huge rates on the vehicle. And so, again, we designed the procedures to get us there and to help us with that. But if something happened and like an engine 2 of them shut down in different sequences, and the second one wasn't recognized, and flight control didn't know it, and it didn't correctly control the vehicle, and then you could get all kinds of high rates. Or you had things starting to blow up in the back, taking one engine out after another. Those probably were not going to be survivable cases. And then the last thing that were always a concern, we had what we call black zones. Now, I'll show you some cards later that'll show you how we improved those. But a black zone, by definition, is where the G loads or the Q bar during the entry were too high for the orbiter to handle, and it either resulted in loss of control or actual vehicle breakup. And we could define these pretty well by analysis, especially after this point when we had a lot of formal engineering rigor in the program. And so we'll talk a little bit about black zones at the end when I show you the capability cards and how it improved. In my experience, when I was flying or working with these, which when I was well, actually, I think I was in safety when we flew 93, but STS 93 was the worst. And we actually offloaded some OMS to give us some better survivability in these black zones. Okay. So the first thing we're going to talk about is how do you kind of organize these things and take a look at them. And what really drives this are the dynamics of the 2 trajectories. So your nominal and tau trajectories, and actually, in tau you'd still be doing a nominal really. We're in one category, and that kind of was an uphill climb, and then hump over the top, a little bit of a downhill toward the end, and then straight flat. In other words, you're either climbing or accelerating horizontally or a little bit of both. And if you were around for the RTLS briefing, you know that doesn't hold for RTLS. Once you board RTLS, you're nose up pitching, you're lofting up as high as 400,000 feet. You're still essentially still heading down range, although a lot slower than you were used to. You flip the vehicle back around, thrust backwards, slow you down, start this really high-speed plunge that eventually kind of hits its max value when you stop moving away from the cape and start moving toward it, which is VRAIL 0 over here on the RTLS contingency on the right. And then you kind of do a scoop out and then eventually pitch the nose down, separate from the tank, and get back to the cape. And as you might imagine, those two trajectories had very, very different dynamics. So that's why contingency aborts were broken into two groups. And you'll see there's two sets of contingency cards. There's a card labeled contingency abort. That's for the nominal and TAL type trajectories. And then we had the RTLS contingency card that was strictly for you who have just aborted RTLS and you've had an even worse day. Okay. Any questions so far? Okay, so what I want to talk about now is there were basic objectives for each contingency abort maneuver. Every one of them that you'll look at will either have all of these things in it or most of these things in it. So the first one is for the two engine out cases. You try to use the thrust on the remaining engine to essentially optimize the resulting entry and recover the orbiter. And I say recover the orbiter if it was possible. And we'll talk about when that was. So you use the thrust in some fashion to either give you a better entry, even if it was going to result in a bailout, or we would use it to try to get us over to a landing site later on in the program. The other thing that would always happen, you had tons of ohms propellant on board, full load you were going to carry to orbit. You wanted to get rid of that for two reasons. Number one, it would pull the orbiter center of gravity really far aft and actually make the pull-out problem really, really bad. The flight control system wouldn't be able to handle it if your center of gravity was too far toward the back. And so one of the ways to move your CG forward and getting it into a good range for controllability was to dump all that ohms propellant, and we'll talk more about that in a few minutes. Of course, the number one thing after that is separate from the tank as safely as possible. Especially with some of the three engine out stuff that wasn't always guaranteed, but we really tried to make sure that we got away from the tank and there was no collision. And then of course, depending on where you were in the sky and what had happened to you, you had some kind of resulting trajectory, which could be anything from not too bad to really terrible. And you had to pull out from that and then fly the orbiter to a landing. Number one objective was to get to a bailout. Number two, get to a landing if you could do it. And I've already mentioned that before bailout, we had to ditch. We didn't really think much that was going to be survivable very often. Now, most things that we did in NASA, we always had a factor of safety. Not here. Here, the crew's survival is at stake. And so because of that, we pushed this vehicle straight to zero factor safety. In other words, just took her right to the margins, structurally, aerodynamically, flight control-wise, every other way to make these work. So we talked about the contingency ohms dump, and you can see over here in this drawing, I'm showing you a picture of it. The maximum ohms load could be as high as 24,000 pounds, and to get to orbit or land, if you were going to do that, you had to get the tanks down below 22% a maximum capacity. The big key for contingency aborts is the next bullet. You had to have the orbiter CG forward of 1109 inches, or you probably weren't going to maintain control. It just overwhelmed the flight control system. Now, how did this contingency abort start? When we were manually flying these, the crew would go here and actually, when we automated them, to a software spec called Spec 51, and they would essentially do an item 6 execute and then an item 7 execute. And as soon as they did that, this contingency dump would start. Now, this picture over here this is a really kind of a 2-engine case, but I didn't put the SSME on here just because I wanted you to see the contingency, the dump and how it's going. And so again, this is really not propulsive. it may be helping you a little bit. It's really to get the weight off the orbiter and to get the center of gravity in the right place. So that's the contingency stuff. The other thing that became essential to you for the 2-engine out cases is something called single engine roll control. If you'll look over here on the bottom of the right, you'll see that what we did to make the orbiter pitch, roll, and yaw was essentially use different engines and mix them together, mix the commands together to make the maneuver happen. If you look at how the engines were controlled, there was a thrust vector control actuator, pitch and yaw on each one. You can see the orientation here. Okay, so if you had 3 or 2 engines, you could do all your maneuvering strictly on the main engines. But what do you do when you're down to 1? Because if you're down to 1, the only thing it can really handle is pitch and yaw. And so what we would do is we would hook up the Ohms propellant to these 24 aft RCS jets, and we'd also use the forwards if we needed them, right up here. And they would fire and perform roll control for the vehicle. Well, how does that work? Well, if you stop and think about it, the center of gravity for the vehicle is actually down here in the tank. So if I apply a torque here, or up, down, whatever, however these fire, I can make the vehicle roll around that center of gravity. So it was always essential that you got single engine roll control set if you were in a 2-engine case, and this is one of the reasons why it had to use this kind of a scheme to make it all work. Okay, I've already explained that part. Any questions there? Okay, so we're going to start with 2 engines out because those are the only ones that you can really affect any of the trajectory on. And just from a basic big picture standpoint, and this is again looking at the nominal type trajectory, there were 2 basic approaches that you had. For the early engine outs, what you need to do is you need to get higher, and you need to do that partially to get the Q bar down low so you could separate off safely, and then the other thing was to try to help you out, give more space, if you will, to enter. But the real thing was the Q bar itself. But if you're up here, kind of at the top of this hump, you're not really moving down range very fast. If you have 2 engines out here and you just point the nose up in the air, it's really not going to help you very much. In fact, it's going to, from here on out, if I right here, if I just push the nose up, it'd be like throwing a ball straight up, and it's going to come straight back down. It comes back even harder. And so what you do here in this regime, in a little later regime, is you actually thrust down range. What does that do? It adds more horizontal velocity. And instead of the entry being really steep like this, which is going to result in a lot of G and a lot of Q bar, you try to shallow it out like this so that you're not pulling as many G's and you're not hitting the high Q bars that you would otherwise. So when we look at the cards, you'll see these 2 different types of approaches used depending on where you are in that trajectory. Now, the other thing that we utilized, and this was kind of later in the program, we started realizing and getting more comfortable with these techniques and refining them more, and we started looking at, could we actually try to pull off a landing somewhere? And it was dependent on the actual inclination of the flight, because what we started looking at first of all was Bermuda for 39 degrees. The trajectory kind of goes out here like this, and it turns out right in this area right in here, if you had something happen, you could actually steer over to Bermuda. We also realized once we had this one in place that when we started flying ISS, we're flying 51.5 degree trajectories and the lines going up the coast like this, and we had all these military airfields, primarily anything with a long enough runway that we could maybe pull off a landing over here. And the way we did that was common to both landing at Bermuda and landing for an ECAL, and it was using something called contingency yaw steering. And so what we did, and you'll see this in the manual procedures, but this is what the automation did as well. And actually, I'll tell you that when we automated the 2-engine out stuff, all we really did was take the manual procedures and put them in software. They really didn't put a lot of analysis trying to see if they could tweak anything. They just automated it. The 3-engine out, they took a different approach, and it's a lot more fancy and smarter than the 2-engine out scheme. But what we would do here is we would pitch the nose up to 60 degrees, and this is right side up, but actually be upside down sometimes. And then we would yaw 45 degrees out toward the landing site. And you just hold the attitude until you watch the Q bar, which the vehicle would calculate. And when you saw the Q bar starting to increase, which meant you needed to get the tank off pretty soon, we would yaw back in, nose forward, and then pitch down and perform a high rate SIP and actually roll heads up if you needed to. Once we automated these, the yaw steering was controlled by software. Again, it was done manually at first, and it kind of depended on the type of abort, and it would actually look at where the second engine failed, was I in a window for any place, and then it would look for a yaw steering enabled entry on an Ascent trudge display, and I'll show you that in a bit. And if you had those, the vehicle would do all this stuff automatically. ET SIP. There were 2 types of separation techniques that we used for contingency aborts. Now, we talked about the RTLS and using an alpha -2 SIP, and you'll see that we actually brought that over and used it for the contingency aborts. But we also have another one, because some of these contingency aborts would happen in regimes where Q bar was less than the 2 pounds per square foot that you really needed to get the tank off the vehicle using aerodynamic force. And so what we would do with that one is we still had a running main engine, and we would literally pitch forward at 4 degrees per second. And once that was established, the crew would punch for the fast SIP switch, which would shut the main engines down and then pop the tank off. And so really it's a good analogy of that is we were literally just kind of pitching the tank off using inertia to get the tank away from the vehicle, because as soon as the orbiter comes off, the RCS jets are going to start firing and pushing it away. And hopefully the tank goes on its merry way and it doesn't hit you. The other type of separation when we had Q bars that were 2 or higher was just to pitch down and hold alpha -2, shut the engine down, SIP off. And just like we would for an RTLS. We always call this one over here with the pitch down kind of maneuver, the high rate SIP, and then the other one we would do is the alpha -2 SIP. And what you're going to see when you look at the procedures is they're not called out by names like this. They're just going to say, do this thing. We're going to pitch down at 4 degrees per second, or we're going to pitch down to some alpha. Once I've got the tank off, just like an RTLS, the next thing you're going to try to do is pitch the nose up to a high angle of attack to recover lift as quickly as possible. Now, because we're in a contingency case and because we're dealing with much higher both flight path angles and aerodynamic forces and G levels, we're going to try to recover lift a little faster than we do for RTLS. So we actually, depending on the Mach number, would pitch up as high as 58 degrees. And again, it might pitch a little bit lower than that. It was Mach number dependent on exactly where it would go. But you'd pitch up and you just simply hold that alpha. And as the orbiter started falling into the atmosphere, lift would start increasing. That would automatically start kind of a pull out, and the G levels would start going up. And so once the G level hit whatever you were going to use for a maximum value, and actually the vehicle calculated that, at 1 G, it snapshotted how fast you were falling. We call that the altitude rate, or H dot. And it would essentially calculate from that the G level that it was going to use for the pullout. It would pick the highest one that it could, especially if you're in these, if it's picking a high number, it's probably going to tell you that you're also going to have a lot of Q bar as well, because you wouldn't be pulling that much G if you didn't have to. And that's the trade-off that you always make. If you pull more G, you're trying to pull more, you're trying to use up more of that aerodynamic force and put less load on the vehicle from an aerodynamic standpoint. If I use less G, well, I'm going to put less structural loading from G acceleration on the vehicle, or G loading, but I'm going to take more aerodynamic loading. And so that's the trade-off you're making through these. And if you get lucky, you don't hit the max G level and you don't go past the max Q bar, and you actually get through the regime. And then once you get outside of that, it flies an angle of attack that's a function of Mach number. And then the other thing too is you generally would have to fly out some cross range. And so what you would do is you would essentially look at how far off the nose it was, and then roll into a bank angle that was twice that. So if, for instance, if my landing site was 30 degrees off the nose, I'm going to roll into a 60-degree angle of bank toward that landing site, and I'm just going to play that del as all the way until I finally, hopefully, take all the cross range out, and I'm essentially about wings level again. How did the crew know whether or not they were going to make it? There was a cue card they had in the cockpit that essentially told them whether they were high or low energy, were you on range or not. And then MCC, of course, was using actual tracking telemetry data and computers to actually calculate the energy and the range and help determine if the landing was possible. And if they didn't think you were going to make it, they were going to tell you to prepare to bail out. I'm not going into detail in the bailout system, but essentially I'll talk a little bit about the bailout autopilot here in a little bit. The idea was to put the orbiter into a glide down here in the bottom right. You can see you blow the side hatch, you extend this pole. The crew actually would have chutes on, they'd hook up to this pole, and then they would just essentially jump out the hatch. They had a little attachment that would keep them on the pole till it spit them out. And the sole purpose of this pole was to get them down below the wing when it released them, so they wouldn't come up and hit the wing after they jumped out of the hatch, which probably would normally happen. Okay. So here's, we're going to talk about the bailout autopilot and how you executed that. And this is, over here on the left is the cue card. We're going to talk about the procedures. We're going to use some of these switches on the eyebrow panel up here at F2. Here's the abort rotary, and that's actually part of what we used to get the bailout autopilot working, because we had to use stuff we already had in the orbiter. This is the RHC, which is a rotational hand controller. That's like the stick in an airplane. And then we'll talk more about the alpha Mach and all that, but essentially, and then this graph over here, this view over here, shows you a cutaway view looking at the pole. This part right here is what would be down next to the side hatch, and then of course this would extend out. This is the part that would extend out after they blew the hatch. This thing just kind of really shoots out, and then the crew would hook up in here and jump out, and it would carry them away. Okay, so the very first thing that you had to do, you had to fly yourself so that you got below Mach 1. And once you did that, you went pitch roll and CSS up here, and you're manually flying, and you make sure you're in Ops 305 if you're not already there. And then first thing you want to do once you do all that is make sure the body flap and the speed brake are in auto, so you don't have to mess with it, and they're going to keep the vehicle stable. And then the whole purpose of this thing is to be in a stable glide at about 190 knots, somewhere between 185 and 195. And what you see here to the right of that is a phi 0, so that's, you want to be wings level. That's what that's telling you. And then once you were there, the next thing you would do is go rotate the abort rotary to the ATO position and push the abort PBI. And when you did that, the autopilot for bailout would be engaged. And then once you had it engaged, you would essentially go back to auto so that it would hold the vehicle for you. And then this is the flight controller power controls, the RHC and actually THC. But the reason that the pilot and commander are both going to turn that off is so they don't kick it on the way out, because if they do, they run the risk of kicking the flight control system back into CSS. That's manual steering, and the idea right here is you're leaving, so there's not going to be anybody to manually steer, and you don't want to do that. So you turn the flight control system power off so you can't accidentally kick the system back out when you want it to work. Okay, that's 2-engine out in a nutshell. So any questions about any of that? So, okay, so for 3 engines out, of course, the big difference is I don't have another engine to do anything with, right? So you're kind of stuck with what you got. No thrust left, and that means for most of the regimes, you're going to have, you start falling into the atmosphere fairly quickly. The Q bars are going to start rising, and the G is going to start rising. You have a very heavy tank, and the only thing you have left to maneuver with are the RCS jets. Now, believe it or not, you could muscle this thing around for every scenario I was involved with. It might not be great, might take you a little while to get over, but you could actually, even if you were heads down, roll it heads up, and then do what you need to do. And then, of course, you want to get off the tank as quickly as you can, as safely as you can. We still had the same techniques. The alpha -2 SEP was kind of dicey, but the high rate SEP, but fast SEP, which I'll explain in a minute, was always used in every contingency abort. Essentially, it was a really fast separation from the external tank compared to what would normally happen. And then again, the pullouts, NZ hold, Mach alpha schedule are exactly the same as they are for 2-engine out. So the big difference here is, we'll take a look at some of these maneuvers because they're kind of interesting, is that you have the RCS jets. Everything's done on the RCS jets. Controllability is not as good. You can't move the orbiter as fast. And if that should tell you anything, it's that if you're in a 3-engine out contingency abort, and especially if you're flying it manually, the crew has to be on top of it, and they have to be moving very quickly to get it all done. You don't have time for any confusion, anything like that. You just got to get on it and get it done, and then do the best you can. The interesting thing, and this is a good point to talk about how we did these maneuvers, the way the RHC was mechanized made it easy to sometimes cross control yaw and roll and even pitch. And so when we design these maneuvers for manually flying, we always design them to fly one axis at a time. And part of that was to make sure that you did exactly what you intended to do and didn't introduce either yaw into some maneuver you didn't intend to, or roll in maneuver in some you didn't intend to. And so it's one axis at a time, whether you're 2-engine out or 3-engine out. That was the way we did all those. Once we automated the 3-engine out software, it could actually figure out, it would know where it was, it would know what kind of targets it needed to hit, and it would figure out the shortest way to get into that position that it could execute. And so it would use coupled access maneuvers. And as you'll see on the cue cards when we look at them, that meant you didn't really know what exactly it was going to do. You had an idea of where it was going to go, but you didn't really know what it was going to do. So it was kind of hang on and pray and follow your cue cards. And if it was in some really bad regions and it knew it could get away from the tank and needed to get away from the tank, the first thing that might happen is it just goes boom and it blows the tank off. Because here in the 3-engine out, everything is automated. Everything. Okay. I'm going to stop right here, and we're going to come back. Let's take 5 minutes out for a bathroom and water break. And then we'll come back because it'll probably take us another 20 or 30 minutes to go through the rest of that. Okay?